Longest nice subarray. You're given an array nums consisting of positive integers. We call a subarray of nums nice if the bitwise AND of every pair of elements that are in different positions in the subarray is equal to 0. Return the length of the longest nice subarray. Okay, let's walk through these two examples and confirm that what the explanation tells us is correct. So I'm going to write down the bitwise representation of each of these numbers. Okay, so I've written down the numbers for example 1. I can confirm that these three numbers do form a nice subarray because at each position there's at most a single set bit. I can also confirm to myself visually that this is the longest nice subarray. Great, now let's walk through the second example. Okay, and here the least significant bit is always set, so we can't have a nice subarray of length greater than 1. So output of 1 makes sense. Okay, now I have an idea for how to tackle this problem. So first, I want to iterate through the numbers, and I want to try to apply a sliding window approach. Whenever I add a new number to my sliding window, say 10, I want to identify the conflicts, the numbers that conflict with 10. So this is 10. We can see in our little diagram that both 8 and 3 conflict with 10. Any number that is or comes before 8 can't be with 10. So that would lead me to throw out all these numbers if they haven't been already discarded in the sliding window, leaving me with a remaining sliding window of just these two numbers. Now fortunately, the sliding window itself represents a nice subarray, so throughout this process we're just going to keep track of the length of the longest sliding window, or the length of the sliding window at any point. Alright, so let's start by defining a data structure to keep track of these set bits. This data structure should have length. See, I wrote length 6 because of 48, so let's just do that. Max length. It's called bits, the data structure. And I want to store in each index just the index of the number of the greatest index number that has a bit set at that position. So we'll write -1 since we haven't processed any numbers yet. All right. So next step is to initialize our sliding window, and with each time we process a number, we're going to want to update. We're going to want to first update our sliding window, and I think actually that's all we need to do. So let's define the bounds of our sliding window. So left, start at 0, so right, can actually just loop through each value and right. Okay, so when I add right in, I want to look in bits to see any conflicts. So I'm going to loop through each position in the given number. Maybe it's a little easier if I do this. So position, we can use like a bit mask trick to see if the number at this, if the bit at this position is set in nums or in num. Or we're going to define this variable to be the index of conflict, or the greatest index of conflict. So here it'd be like 2 for the number 10. So in bits, at a given position, we're just storing the index of the number that has a bit set in position. So now that we have found all the conflicts and found the greatest index conflict, we can update left. Right, and also we want to modify our data structure after we process each position. Okay, now we just need something to store the answer. So I'm thinking if I'm off by 1 here. Left is the index of the greatest conflict. Okay, so it's like inclusive of right but exclusive of left. So I'm just gonna write -1 here. Okay, let's give this a test run. Oh, awesome. Let's submit. Yay!